Welcome to day 6 of researching for our colonies. This is the Heisenberg-Russell diagram. In your research, you may have seen this or read about this. Look at this diagram. There are 2 questions I need answered in the beginning of class tomorrow. What does this diagram have to do with electromagnetic radiation? And why are the stars the same color as a rainbow? Be prepared to answer these questions at the beginning of class. This diagram shows temperature and color graphed together on the x-axis, and the y-axis is the luminosity or the apparent brightness of a star, and the size of the star. Notice that the brightest stars on the x-axis is closest to the y, and the largest size at the top of the y. The dots represent the stars we know. Remember the video on the first day about color and temperature of a star? The hottest stars were blue, but this graph goes to purple. Why didn't they talk about the purple stars? Well, that's because we haven't found one yet, but according to research and math, they should be there. You may notice that throughout the PowerPoint, there are websites under pictures and certain statements. That's called learning through osmosis. Just kidding. These are examples of citing source information in your work. Remember it, you'll be using it later in class. Things we need to know about orbits. The orbital plane and Kepler's laws. The orbital plane is a relatively narrow zone expanding outwards based at the Sun's equator as its center line, containing all the planets. If you're not exactly sure what this means, that's okay. I'm going to give you an example or things to picture to help you understand. Imagine or think of a cake, a round cake, the kind with fruit on the top, and how there's usually a big piece of fruit in the center of the cake pushed about halfway down. This will represent the Sun. The other pieces of fruit are at different places along the top. Some are closer and some are at the outer edge. These pieces of fruit are like planets. Now in this example, the orbital plane would be the frosting. On these next slides, I'm going to introduce Kepler's 3 laws. Kepler's first law states that the orbits of the planets are ellipses, with the Sun at one focal point of the ellipse. Kepler's second law states that the line joining the planet to the Sun sweeps out in equal areas in equal time as the planets travel around the ellipse. Now, remember, this PowerPoint is online, so you can go back at any time and review this material. Kepler's third law states that the ratio of the square of the revolutionary periods for the 2 planets is equal to the ratio of the cubes of the semi-major axis. A little confused about Kepler's law? I know I wasn't the first time I saw them, so do not panic. Here are 3 videos to help you understand these laws. You can find them in the PowerPoint or in the resources online. Now the first law I'm not going to play for you, but it's in the PowerPoint. And if you need it, it's there. But I'm going to give you a hint. We don't orbit in a circle, it's an oval.
Thanks to the meticulous astronomical observations of his colleague and employer Tycho Brahe, Johannes Kepler was able to test several rival hypotheses for how the Sun and the planets are arranged in the solar system, eventually leading to his 3 laws of planetary motion. In 1609, he published the first 2 laws in a book called Astronomia Nova, which focused on the movements of the planet Mars. Mars was something of a conundrum. Its observed motions didn't match any of the proposed models of the solar system, which involved circular orbits. Kepler's first law states simply that Mars travels in an elliptical orbit, with the Sun at one focus of the ellipse. Although he chose to list it first, Kepler only came to this conclusion after figuring out his second law, which says that if you draw a line from the Sun to Mars and wait a fixed amount of time, that line will sweep out a certain area as Mars moves along its orbit. What Kepler noticed was that this area is exactly the same no matter where in the orbit you are. This is often phrased as Kepler's equal area and equal time law, and this law works because Mars doesn't move at a constant velocity. It speeds up the closer it gets to the Sun. So if Mars is approaching perihelion, the point in the orbit nearest to the Sun, it's traveling faster than if it's at aphelion, the point that's farthest away. In the first case, the line connecting Mars to the Sun is very short, but because the planet is moving faster, it covers a lot of distance. In the second case, the line segment is much longer, but Mars also moves more slowly. Either way, the area swept out in a fixed amount of time is the same. Kepler and his contemporaries could see that Mars doesn't move at a constant rate, but they didn't know why. This inverse relationship that Kepler proposed between distance from the Sun and orbital velocity could explain the puzzling observations of Mars' movements, but only if the orbit is an ellipse. A circular orbit would mean no change in distance from the Sun with time, and thus the velocity would be constant as well. These two statements, that Mars travels in an elliptical orbit and that its speed varies so that the Mars sunline sweeps out equal areas in equal time, were generalized to include all planets in 1621, and they constitute Kepler's first and second laws of planetary motion. The second law, it turns out, is also a consequence of the conservation of angular momentum, which was not a concept known to Kepler in the 17th century. Angular momentum is a measure of the amount of rotational motion in a body or system of bodies, like Mars and the Sun, and in the absence of outside forces, it's a fixed quantity. This implies a trade-off between the distance at which Mars orbits and its velocity, like Kepler noticed. Just as an ice skater spins faster after pulling her arms closer to her body, Mars has to move faster when it gets closer to the Sun. Kepler's statement that the area swept out by the Mars sunline is constant is equivalent to the statement that angular momentum is a constant as well. That is to say, that it's conserved. Kepler's first and second laws of planetary motion appeared in their earliest form in 1609 in the book Astronomia Nova. They state that 1. Planets move in elliptical orbits about the Sun, which sits at one focus, and 2. A planet's orbital velocity varies over the course of one revolution, such that a line drawn between the planet and the Sun will sweep out equal area in equal time, wherever in the orbit you are. Kepler published his third law 10 years later in his 1619 book Harmonices Mundi, or The Harmony of the World. By sifting through observations of how the planets move in their orbits, he noticed something curious. The time it takes for a planet to orbit the Sun once, its orbital period, p, is related to its average distance from the Sun, its semi-major axis, a, in a very specific way. The square of the period is proportional to the semi-major axis cubed. In fact, if we choose our units carefully with the period in years, the time it takes for Earth to go once around the Sun, and the semi-major axis in astronomical units, or AU, the distance between the Earth and the Sun, about 150 million kilometers, the proportionality becomes an exact equation. The square of the period is equal to the semi-major axis cubed. Let's try it out. Earth's semi-major axis is 1 AU, because that's the definition of an astronomical unit. Mars is farther from the Sun. It has a semi-major axis of 1.524 AU. We can use Kepler's third law to figure out how long it takes Mars to complete one orbit around the Sun. That is, how many Earth years make up one Mars year. The semi-major axis 1.524 AU cubed equals 3.54, and the square root of that gives us Mars' orbital period, 1.88 Earth years. Sure enough, Mars takes 687 Earth days to orbit the Sun, which is 1.88 Earth years. And this works for all of the planets in our solar system. But what if we don't want to use astronomical units and Earth years, but something more conventional, like kilometers? Then we have to unpack Kepler's equation a little bit more. In modern notation, it becomes p squared equals 4 pi squared over g, the gravitational constant, times m sun, all multiplied by a to the third power. That term before the a cubed is the constant of proportionality in Kepler's original equation. M sun is the mass of the Sun. And to be completely accurate, the equation should say m sun plus m planet, the mass of the Sun and planet together. But because the Sun is so much more massive than even the biggest planet in our solar system, Jupiter, the mass of the Sun is more than 1,000 times the mass of Jupiter. The extra mass added by m planet is tiny compared to m sun, and doesn't make much of a difference. G is the gravitational constant, which might look familiar if you've ever seen Newton's law of gravitation, which states that the force due to gravity equals G times big M times little m, all over the distance squared. Actually, you can derive Kepler's third law from Newton's law of gravitation. Although, of course, Kepler didn't know that. By setting the force of gravity equal to the centripetal force, the force the planet feels because it's revolving around the sun. Let's consider a circular orbit first, because that's the simplest case. The centripetal force depends on the planet's speed, v, which for a circular orbit is constant. F centripetal equals mv squared over r. Setting these two forces equal to each other gives us a relationship that simplifies to v equals the square root of g times m over r. Now, since we're considering a circular orbit at the moment, we also know that there's a relationship between the speed v and the orbital period p. The planet has to go around the whole circumference of the orbit, 2 pi r, in the time p, so the speed must be equal to 2 pi r over p. And if we substitute that into our force equation from before and use the semi-major axis a as our distance from the sun, now we're back to elliptical orbits, we have 2 pi a over p equals the square root of g times m over a. After some rearranging, we've gotten back to Kepler's third law. That is, p squared equals 4 pi squared over g times m sun, all multiplied by a cubed. This expression is especially informative because it relates two values that you can measure with a telescope: distance to the sun and orbital period to the mass of the sun. And that's how we know how heavy the sun is. Even better, it works for all kinds of orbiting systems. You can find the mass of the Earth, for example, by rewriting the equation using the distance and orbital period of the Moon. The Moon's orbital period, p moon, is 27.3 days, or 2,358,720 seconds, and the semi-major axis of the Moon's orbit, a moon, is 384,400,000 meters. G, as usual, is 6.67 times 10 to the negative 11th meters cubed per kilogram per second squared. Solving the equation using these parameters yields an estimate for the mass of the Earth of 6 times 10 to the 24th kilograms. Any planet with a moon can easily be weighed this way, and it's all thanks to Kepler's third law.
Here's tomorrow's assignment. If you want to start researching on it, for this assignment, it's your choice, but you'll be working in groups tomorrow, and you cannot be grouped with the same people as you were in the last group assignment. But you still have work to do for this lecture. There's an online quiz to verify that you have watched this. Thank you for watching, and don't forget the 2 questions we need answered in the beginning of class tomorrow. What does this have to do with electromagnetic radiation, and why are the stars the same color as the rainbow?